Okay, imagine this. You put a pan on a stove, you crank the heat, and the pan gets hot, fast, normal, right? Now, here's the weird part. On an induction cooktop, the pan is sizzling, but the glass surface underneath, it's not ripping hot. In fact, you could place a piece of paper between the stove and the pan, and it wouldn't even singe. Welcome to the smart side, the channel where we peel back the plastic on how everyday tech actually works. And I promise, by the end of this, you'll understand exactly how induction vibrates a pan into high heat, without the stove ever breaking a sweat. All right. First, a quick reality check. Most stoves are middlemen. They heat something up, and that hot thing eventually heats your pan. Gas uses a flame. Electric stoves use a glowing coil. Even those sleek glass top electrics, there's a massive heater trapped under that glass. The glass gets hot because it's literally standing in the line of fire. Induction is a total departure from that. With induction, the cooktop isn't trying to be a heater. It's trying to be a transmitter. And the way it sends energy isn't through heat. It's through high-frequency electromagnetism. Here's what's hiding under the glass. A tightly wound coil of copper wire. When electricity surges through that coil, it creates a magnetic field, but not the steady kind you'd stick on a fridge. This is a flipped field, vibrating back and forth thousands of times every second. And a vibrating magnetic field has a unique superpower. It can force electricity to move inside any metal it touches. So when you drop a heavy pan on top, the cooktop reaches through the glass and starts violently shaking the pan's electrons. They swirl in frantic little loops. Engineers call these eddy currents, but you can just think of it as electrical friction. The cooktop is generating a current directly inside the metal of your pan. And here's the clincher. Every metal has resistance. It doesn't want those electrons to move. As the electrons fight to swirl, that resistance creates heat. Suddenly the pan isn't just holding heat. The pan is the heating element. That's the big mind blow. Induction doesn't wait for a burner to get hot and transfer the energy. It beams energy straight into the atoms of the pan. So now the obvious question, if all this power is surging, why is the glass still cool enough to touch? Because to a magnetic field, glass is basically invisible. The field sails right through it without grabbing anything. Glass isn't conductive, so it can't host those swirling currents. In plain English, the cooktop is aiming at the metal. The glass is just the window it's looking through. Now, small but important detail, the glass will get warm eventually, but that's just backwash heat coming down from your sizzling steak. It's borrowed heat, not generated heat. And once you see that distinction, the mystery of the cool stove disappears. Now let's talk about that turbo, speed. With gas, half your heat escapes around the sides of the pan. With electric coils, you're wasting energy warming up the air. Induction skips the waste. It concentrates 90% of its energy exactly where you want it, the very base of your cookware. More power goes into the boiling water, and less goes into accidentally heating your kitchen. It's not just fast, it's surgical efficiency. Okay, quick check. If induction uses magnets, why doesn't it work with my favorite ceramic or aluminum pans? Because the internal friction we talked about requires a specific target. It needs a material that responds strongly to magnetic fields, usually iron. Aluminum? The field just ignores it. Copper? Too slippery for the field to grab. This is why you need induction-ready cookware. Essentially, any pan that a fridge magnet will stick to. If the magnet sticks, the invisible stirrer can work its magic. Now, how does the cooktop actually control the temperature? This surprises people. Induction stoves don't really have a low flame. They control the intensity of that magnetic field. More power means a more violent shaking of the electrons, which means an instant spike in heat. Because there's no massive red-hot coil that needs to cool down, the response is instant. You turn the dial down, and the boiling stops immediately. It's a dimmer switch for pure energy. Now, safety. If it's using high-power magnetic fields, is it safe for us? In short, yes. The field is incredibly short range. It drops off to almost nothing just a few inches above the surface. Plus, most induction stoves have a brain. If it doesn't detect the right kind of metal, it simply refuses to turn on. Lift the pan and the energy circuit is broken instantly. This is why induction is the king of the cool kitchen. No wasted heat bleeding into the air. Now, why do people still burn things if it's so smart? Because induction is a race car. If you're used to the slow ramp-up of a traditional stove, induction will catch you off guard. It's like moving from a bicycle to a motorcycle. Same road. Very different acceleration. You might even hear it working. A faint hum, a high-pitched whistle. That's just the physical vibration of the metal layers in your pan reacting to that magnetic shaking. Thicker, high-quality pans are usually quieter and distribute that induced heat more evenly. Alright, recap time to lock it in. Induction doesn't heat the stove. It projects a vibrating magnetic field. That field forces electrons inside your pan to swirl. The pan's internal resistance fights that movement, and that fight creates pure, direct heat. The stove stays cool because the pan is doing all the heavy lifting. It's basically wireless power, not for your phone, but for your dinner. It proves that the pan isn't just a container anymore. In an induction kitchen, the pan is part of the machine. So let's loop back to the start. A sizzling pan on a surface that won't burn you. It's not magic. It's just a more direct path to dinner. Instead of heating the room and hoping the pan gets the message, induction puts the energy exactly where it belongs. And once you see it that way, the mystery is gone. It's a high-tech handshake between a copper coil and a steel pan. So here's a thought to leave you with. If we can move energy through glass to cook a steak, what other clunky tools in our lives are just waiting for us to cut out the middleman? If you enjoyed this deep dive with the smart side, hit the like button and subscribe. It helps us keep the lights on and the magnets humming. See you in the next one.